Swayam Prabha. Digital India. Educated India.
I thank the organizers, Professor Ashwini, Professor Lut, and Professor Sanjay sir for giving me the opportunity to talk of my work on this topic, small carbon clusters, in this conference or discussion meeting on structure and dynamics of chemical systems, honoring Professor Sati sir on his 75th birth anniversary. Thank you. So I thank Professor Tumati for inspiring me for last 2 decades to work on this field. So with this, I'll go to my talk. So I'm working on cold collisions and scattering dynamics, specifically on atom-molecule collisions, atom-ion collisions, and then ion-molecule collisions, and molecule-molecule, neutral-molecule collisions, and molecule and molecule-ion collisions. Our interest is based on, our motivation is based on the ions or molecules detected in space in ISM. So we choose the molecules detected and then study its scattering dynamics with helium and hydrogen molecule or with proton. Today I'll be talking on hydrogen collision with linear carbon chain, specifically C5 and C5H plus ion, which has been detected recently and, in ISM. And I'll be also giving the comparison between the 2 systems in our results. So about interstellar medium, it's a space between stars that contain various particles and matter. It is filled with gases, dust, and cosmic rays and other elements. It goes on cycle in ISM. First clouds will be there, and then stars will be forming, and again goes to the clouds. Clouds could be of diffuse clouds or dense cloud, where you find a hydrogen atom or hydrogen molecule respectively. From clouds, it leads to formation of stars and planets. Again, it loses to form again clouds. So since it is made up of gases, mostly it is 99% of gases, in which the hydrogen, which is maximum, 92% is available or found. Helium is close to 8%, and other gases are 0.1%. So since hydrogen and helium are in large number, our interest is the collision of these molecules or atoms with the species present in space. So we calculate the rate coefficients, and then finally from that we'll get the abundance ratios, and basically abundance ratios we calculate. That's the ultimate aim, to see whether how much is present or how long it will exist. So motivation is there are more than 340 molecules detected in space. I've listed it. Mostly they are neutral molecules. Then there are radicals, cations, anions. Nowadays, even the aromatic hydrocarbons have been detected. And yeah, some of the molecules which of interest are shown here. Mostly they are detected using radio IR spectrum or microwave spectrum. And there exists an ISM, it exists non-local thermodynamic equilibrium, where the collision rates are needed with the colliders, the helium and hydrogen colliders, for calculating the column densities and abundances. So our interest is how to calculate this rate coefficients. So we have chosen, in today's talk I'll be discussing about the carbon chains which has been detected, and there are different carbon molecules being detected: C2, C3, C5, and protonated form of C5. C4 is still not detected. So today I'll be concentrating more on C5 and C5H plus system colliding with the hydrogen molecule. So what we generally do is we just theoretically we compute the potential surface by ab initio method. Then we fit it. If it is with helium, it's easier to fit, easier to get the surface and fit it. Whereas for hydrogen, the dimension is very high, so we have to use machine learning technique to get the surface. And then once we have the reliable surface, we go ahead and compute the multipolar expansion coefficients. From that, we calculate the cross sections by solving close coupling equations. And from cross sections, we go ahead and compute the rate coefficients as a function of temperature. Since the ISM temperature is between 10 to 100 Kelvin, so all our calculations are below 100 Kelvin. Our target temperature is up to 100 Kelvin. So in my first study, I'm going to be explaining about the linear C5 molecule collision with the hydrogen molecule. So we have chosen, so this is the ground. The linear molecule is the stablest one, C5, and then H2. We have chosen the internal coordinates varying with capital R, where R is the distance between the hydrogen molecule and C5 molecule. And there are the three angular coordinates. Theta 1 is the angular coordinate for C5, and theta 2 is the angular coordinate for H2, and phi is the diagonal angle. So with this coordinate system, we went ahead and computed the surface. So we use the couple cluster single and double excitation with the triple extrapolation technique with F12A method with the augmented correlation consistent polarized valence triple zeta basis set. These are the parameters we varied. We assumed it because our target temperature is up to 100 Kelvin. We kept the molecule as rigid rotor. So there are two rigid rotors we are studying. And then the method which we chosen is benchmarked with accurate or gold standard couple cluster technique. But in order to compute the surface, I mean, for getting the collisional parameters, one has to compute the very accurate surface because it could be the surface could be highly anisotropic. So one has to have a dense grid. If you go ahead and compute the surface to get the dense grid, it's nearly 9 lakh points one has to compute, and it will take multiple years to get the surface itself in a standard computer. So instead of, because it's a hydrogen collision, so in order to get the surface, instead of spending time to get the ab initio surface, we use the supervised machine learning technique to get the surface. So we compute the coarse surface by varying the R and other angular parameters, and then compute nearly 11,000 data points, mapping the entire surface at its coarse grid, and then use that data points and then feed it into the machine learning technique and get the full surface. We generate the surface very quickly in this process, whereas to get the coarse grid potential surface, it took a little more than 1 month. So the method is fitting, neural network fitting method is we use different input layers. At least 4 parameters are used as a descriptors, which is R and 3 angular parameters, and whereas we have 1 output layer, which is the potential we calculate, and then we varied 3 layers to get the accurate surface. And there are at least different models one can try. Here, I mean, with the training, validation, testing, we have to keep changing it and then see which model gives the lowest RMSE error. We found that 8:1:1 ratio or 80:10:10 ratio gives the much accurate potential surface. So we choose this ratio of data points. Basically, from the 11,000 data points, we neglect the high energy data points, and neglect means we use scatter functions to fit the high energy points, whereas the important points, the surface, fit it 80%, we use it for training, and then remaining 10% for testing, and remaining 10% for validation. So these are some of the details about the neural network fitting. As I was saying, the high energy points are fitted using scatter function, and then activation function is a tan H function which we use, and then learning rate is fixed at 0.2. And for this, we got the RMSE error is less than 1 centimeter inverse, which tells the surface which got it by neural network fitting is ready for performing the dynamics calculation. This is check. By doing NN model, we went ahead to compute 13,357 angular terms to get the potential surface, which is 80-fold from the original ab initio points. After getting the surface, we got the residuals compared with the ab initio data points, which is plotted here. You can see that the spread is close to the 0 value, meaning it is a reliable surface. So with this results, we went ahead and did the dynamics. These are some of the plots we obtained from the surface. So this is potential surface for phi equal to 0. There is a diagonal angle kept at 0, and then theta 2 is the hydrogen molecule is kept at 90 degrees, and theta 1, which is the rotation of C5 molecule, is varied as function of R. So this is potential surface along with its contour is shown. Similarly, here it is diagonal angle 0, and then the hydrogen is kept at, the C5 is kept at 90 degrees, and then theta 2, the hydrogen molecule rotated, and its contour is plotted here. And this is the diagonal angle is kept at, the diagonal angle is varied, where other two angles are kept at 90 degrees. So these are some contours, and we found that the global minimum is found at diagonal angle of 0 degree, and where theta 1 and theta 2 are at 90 degree, meaning the molecule C5 and H2 are linear position. That's the global minimum. And the energy is found to be, the well depth is found to be minus 193.6 centimeter inverse. So these are some of the plots, just to say how anisotropic the system is. You can see by different rotations, the surface keeps, the contour keeps changing. Similarly, it's more plots, so it tells about the anisotropy, rich in anisotropy in this surface. So after getting the data points using machine learning and ascertaining it's a very reliable surface, we went ahead to solve the close coupling equation. So for that, we want us to have a potential independent of angular terms. So we convert the potential to radial coefficients, which is expanded in bispherical harmonics. So which includes Clebsch-Gordan coefficients, and then spherical harmonics of each the C5 and H2 molecule. So we got the V lambdas as function of R and plotted here. You can see that various V lambdas are plotted, and then the V0 is found to be lowest. With isotropic term is around 91.98 wave numbers, and all our odd values are all even values are all present, whereas odd values are all 0 because C5 system is symmetric. So after getting this V lambda, we solved the close coupling equations using a Molescat code and got the state-to-state integral cross section by putting the boundary condition for the scattering matrix, and cross sections are calculated for various J values. So these are some of the parameters which we used in our calculations. So this is cross section we calculated, and these are some of the results which we got for C5 collision with hydrogen. As you know, hydrogen has both ortho and para hydrogen, where ortho is the spin, both are the nuclear spin are parallel. So one has to calculate separately for parallel spin and anti-parallel spin. So this is plot for ortho hydrogen. This is excitation cross section plotted as function of energy, and it's delta J keeps increasing from 2, 4, 6, 8 is shown here. And in this plot, we have shown for para hydrogen collision with the C5 molecule. Excitation cross section are shown, and here the comparison between ortho and para. So what is to be noted is there are a lot of resonances at low energies up to 10 Kelvin or 10 wave numbers. We see a lot of resonances. It's identified as fetch batch resonances in the system. So this is for excitation cross section, and then we went ahead to calculate the rate constants by averaging the cross sections over the Maxwell-Boltzmann velocity distribution using this equation for both ortho and para collision with C5 molecule. So this plot a function of temperature for delta J equal to 2n. Basically, the n value varies from 1 to 3, and this is for delta J equal to 2, starting from 0 to 4, 6 for both ortho and para. What is to be noted is in this rate coefficients, the ortho values are higher than the para hydrogen rate coefficient values for C5 molecule. And this is some results for de-excitation cross sections or de-excitation rate coefficients for both ortho and para hydrogen collision with C5 molecule for delta J equal to -2, and this is for delta J equal to -10. And we have already at various temperatures we have compared the absolute values of rate coefficients for both para hydrogen collision and ortho hydrogen collision with C5 for say for 2 to 0 or 4 to 0 transition or 4 to 2 transitions. What to be noted is, as I was saying, the ortho values are higher than that of the para hydrogen collision rate coefficients. It's always, the ratio is always more than 1 at any temperature. So once with this data, one can go ahead and compute the column densities and abundance in the non-LTE region. And we made this cross-section value, I mean the rate coefficients values, a function of temperature, made available in the BaseCol database for further use by other astronomers. So this is about C5 system. Okay, so I just summarized about the C5 correlating with the C2 molecule. So we use CCSDT F2LA method with the appropriate basis, which has been benchmarked with the CCSDT method. And then since we are taking the hydrogen collisions, it's very time consuming to get the full surface. So we use a machine learning technique to get the 4D potential surface after making sure the surface is free from overfitting or underfitting, and we went ahead and compute all the close coupling equations and got the rates. In cross sections, we found a lot of resonances, and what we observed is ortho hydrogen rates are always higher than the para hydrogen rates. This is about C5H2 molecule. Then since C5H plus, the protonated form is recently detected, we explored this system recently. So it has been detected in Taurus molecular cloud, this C5H plus molecule. So similarly, the procedure what we employed for C5 is also employed for the C5H plus system. The only difference is here, since the system is non-symmetric, one has to go for theta 2, which is rotation of H2, all 180 degrees. So not just to stop at 90, but you have to rotate all the way to 0 to 180 degrees. So it's more computational data is required. I mean, more data is required for the getting the full surface. So otherwise, the techniques which we employ for C5, we use it for C5H plus to get an idea of how it compares with C5. Although it is ionic system, we still incorporate the same technique which we use for C5. So after fitting the surface, these are the contour plots obtained for C5H plus collision with the H2, and here the global minimum is found to be a T-type structure, not the linear. Whereas in C5H plus with H2, there is a T-type structure as found, where the T2, I mean the theta 2, which is the hydrogen rotation, is 90 degrees, and theta 1, C5H plus is at 0 degrees. And minimum energy, I mean the well depth is found to be 541.54 waves centimeter inverse, which is higher than that of the C5. So this is the contour map for the which tells about the global minimum. It's somewhere here, the global minimum for this C5H plus system. So after asserting the surface is of very good quality, we went on to compute the V lambda values as function of R. Here you can see you have both the the attractive potential and repulsive potentials, and also the odd terms are also appearing because C5H plus is a unsymmetric system, so we expect even the odd terms, lambda terms, also present. So after getting this, we solve the close coupling equations using the parameters displayed here, and got the cross section as function of energy, collision energy. And here we have shown here. So similarly for ortho and parahydrogen, we have plotted here. Here resonance are not prominent, unlike C5 system. And here also we observe the ortho data is ortho. I mean, that is when you compute the rate coefficients, the ortho is always found to be higher than that of the para, which was already seen in as seen in C5 system. Here, so the rate constants, one we obtained is shown here. We have calculated up to 100 Kelvin. This is about the de-excitation rate coefficients for ortho and para hydrogen system. One thing to notice in C5H plus collision with H2 molecule at different temperatures, we plotted it as function of J. You can see that, as I said, C5H plus system has both the odd and even J values. So you can see that the even values have a higher propensity compared to the odd J values. So this is we observe both in ortho and para hydrogen system. This is true for even at different temperatures, starting from 5 to 100 Kelvin. And this table has a lot of data, but yeah, this summarizes what we have studied in these two systems, comparing with the helium. So this is the rate coefficient data computed at various temperatures. So this is the temperature column is here, and then the second column is the helium collision with the C5 system, and helium collision with the C5H plus system, rate constant values at different delta J values. So it's a de-excitation rate coefficients basically. What to be noted is the values shown here, always the hydrogen rate coefficients are always higher than that of the helium system. And among the hydrogen, in both the systems, the ortho is having the higher value most of the time compared to the para. And for helium system, we have taken the data made available by the scientists in the base cold database. So we have used that data to compare it with the H2 collision. So coming to summary of C5H plus with H2, we got the global minimum having a L depth of minus 541.54 centimeter inverse, and the cross sections, the rate coefficients are obtained for both ortho and para hydrogen collision with the C5H plus. As in C5, the ortho hydrogen rates are always higher than that of the para, and in this C5H plus molecule, we found that the propensity for even transition is higher in rate coefficient values. To be frank, we really don't know the reason. Only in this system it showed the even propensity, and comparing with the helium, the para rates are higher by factor of 5 at low temperatures, and that the ratio decreases to 2 to 3 at higher temperatures. So with this, I would like to thank my students, scholars involved in this project. So Ms. Pooja and Apur are here. They presented the poster yesterday, who worked on these two systems. And I would like to thank the sponsors, SERB, CSAR, NSM Supercomputing Facility, specifically Param Smriti from Nabi Mohali, and my institute, IIT Ropar, for support. And the whole thing, whatever we have done, we have generated as a code, which is made available in GitHub, which really helps in getting the automated point surface generation. It does the fitting, and then does the NN ML techniques one can do, and finally the code helps to compute the multipole expansion, and then it integrates with the MolSCAT code. to get the rate coefficient. So these are all automated and made available in this link. And recently we have developed the GUI interface also for getting these parameters. So with this, I would like to thank the audience for listening my talk. Thank you.
Swayam Prabha, Digital India, Educated India.